measurements out, so nothing important is happening yet. Man, I wish I'd discovered that chime sooner. That's way more convenient. Cool. The scheduled lesson today is lesson 8. The topic is depression and canopy storage. This will be shorter than usual, but we're going to use some of the time to re-examine parts of yesterday that I didn't really do justice to. So actually before taking this link, I'm going to do it to get to the right location. Oh, I got to fix the style sheet because that's not what it's supposed to look like. Let's go back to lessons. So I'm going to re-examine parts of lesson 7 because there's some garbage collection that needs to be done to complete that, in my opinion. And then we'll talk about depression and canopy storage, and it's going to be in very overview terms. As I was looking at the two books that I've mainly been referring to so far, that actually neither of them discuss this much at all. I mean, it's almost excluded, and yet these are meaningful concepts in certain contexts. So a lot of what will be presented I have no direct references to as of yet. I think I know where they are, but I don't think they're in my reading material. And then starting tomorrow, we'll actually start messing with some of the software, because at the end of today we will have completed what I consider all the preliminaries of hydrologic processes, so that we will understand all the pieces that are represented in various computational tools. All right, so let me return to lesson 7, and I think it's in So what I've done is I've gone to a reading from 2008, and this discusses the green amped loss model, which is one of the infiltration models that was discussed yesterday. It's not always the most appropriate one, but it has an advantage in that it is loosely based on soil science. So there's a lot of physical concepts that are fairly easy to explain. And I'm going through material that's explained in Chow May starting on page 144, and we may actually visit the actual reading to illustrate some things. So let's look at the green amp model. So we're going to ignore the first part. It's actually illustrating the creation of the model. So to apply green amp, we have to have an idea of what the saturated hydraulic conductivity is, and oftentimes we can infer that from the web soil survey information for study area. We need to have a good idea of the change across the wetting front in saturation. If we can't come up with a good guess for that, actually the one can assume wet and dry and use that as the change in saturation. We need an estimate of the soil suction, which can be obtained from the soil descriptive properties. For example, if the soil has a fairly high clay fraction, the suction is going to be on the order of 1 to 2 meters, expressed as a head. If it's sandy, very sandy, or really well drained, that suction value is not very big, 30 centimeters. So these represent capillary rise. That's what I use when I can't look these up anywhere. I try to determine what the capillary rise would be in the particular soil. Oh, actually it says that right here. The porosity of the soil and the capillary rise are reasonable substitutes for these values. And we need to just be aware that there's going to be overestimation, but we're using a tool that's already an approximation, so I wouldn't be overly disturbed with overestimation. And you need a reasonable guess of the current position of the wetting front. It will work with a value of 0. You'll get results. I personally sort of don't like that. I usually put the initial position of the wetting front a few fractions of an inch below the surface so that I'm not getting infinite infiltration rates. And so here are the model equations. These are taken almost directly from Chow, Mehmet, and Mays. So this first one is that the infiltration rate, script F, at some time t is equal to the saturated hydraulic conductivity multiplied by the suction, soil suction, the change in saturation divided by cap ft, which is the total infiltrated volume. As an aside, the ratio of cap ft to delta theta happens to be the physical position of the wetting front, a distance L. So this delta theta over f of t could be replaced by z for the wetting front, plus 1. And then an update scheme is used where over a particular computational time step of length delta t, we take the smaller of the infiltration rate over that time step, or the rainfall rate, and if the rainfall rate is the smaller, all the rain is considered to be used up by infiltration. We add to it the current value of volume, and that becomes the new estimate. And so in terms of an algorithm, it would be starting at some time 0. We specify some initial condition. We compute the infiltration rate using equation 1, the known value. Then we use equation 2 to produce an update, and we repeat. So here are the computations illustrated in the scripting environment R. Things I'll point out to, I'm actually going to go run it in a second. We use the rate function, which is essentially equation 1. We use the accumulation function, which is equation 2. And there's some examples of how to operate it. It can be done independently or as a nested call, and this gets done a lot right here. And now it's going to use the example that's presented in Chow, Mehmet, and Mays. So in Chow, Mehmet, and Mays on page 144, there's a set of rainfall cumulative values that are provided, and they're provided every 10 minutes. Here is some manipulation to get the various vectors in the correct time units and in useful values. And right here is actually a pretty important one. This is how the incremental rain is computed from that cumulative rain. If you recall back earlier, that's going from the blue curve to the red step functions. And then the green amp calculations are done right there. And then it plots everything. The plotting is just kind of cool. So there's what comes out. So if you had a need to do a green amp infiltration calculation, if you go to this one, green amp as a script, open with RStudio, and then wait, and then wait some more, and wait even more, this should work. And so now when I run the entire file, if you take a look at what's presented in the textbook in that example, you'll see that this essentially is the identical calculations. As examples go, I mean, it's nice in that you can make calculations, but it's not the most useful example in the world because the authors have selected a time-stepping scheme that just happens to work out right. And in many cases, that's not suitable, and you have to take a slightly different approach. And so I'll go to that slightly different approach. Page 144. So it takes me a little while to find my infiltration. And I want to find the correct. So what I just did was a version of this. There's a flowchart for doing all the calculations. And this is the example that was used. And so the trick of the example is the use of a time step of 0.167. I think they were using it in hours, so that's actually a time conversion. You need to be, if you're going to do this yourself, you need to be aware of that delta t choice. It's somewhat sensitive to that, especially if it's a data analysis approach. And this diagram, sorry for the large tail. Are you done yet? Look, I'm fine with you. Just sit down, okay? Sit down. Right there. You sit down there, you won't be in the way. And yet you will be in the way. So, I mean, that's a win for both of us. Okay, so there is the green-amped method in one example. So if I scroll back up here, there is an explanation that I found pretty useful that I've now lost it. This infiltration calculation can actually be replaced with a Newton's method, and then it becomes irrelevant what the time step is. And let me see if I can find where that was communicated. If not, I'll just mention it in passing. Yeah, it's not going to show up for me now because I have an audience. Rats. Yeah, it's not a searchable document, of course. And it's not a complaint. I mean, I didn't have to pay for this. Someone else had scanned the book, put it up on a web server, and that's kind of just a cool thing. Unless you're the original author of the book and you care about royalties. Dr. Mays certainly cares about royalties, but this book in his mind is old, and he would rather people just read it and use the content than worry about getting paid for it. I can't find the part here I was looking for, but there is a mention. At some point it should say this is a nonlinear equation. I can't find it. That's may actually be in the wrong part of the book. Okay, well that's neither here nor there. If you have to do it yourself and you want to make it even more general, you can take it from this data science point of view where you're analyzing time series inputs and create the green amped entirely as a function where you provide a particular input. You still have to know where the water table is, and then it can, the wetting front, and then you can apply a Newton's method approach, and it can deal with the time stepping by itself. All right, so that is, I just uploaded the script this morning, so it is available on the class server if you want to take a look at it. And if there becomes a need later in the class, we may do this as an exercise. But what it does is it conveys the computational information. Okay, that's actually kind of what I wanted to finish up relative to that. The other thing is I wanted to mention the mechanisms that water can get into the ground fast. And here's some road cuts. And here we see a macro pore, or a large path for water to get into the subsurface. And then here's some where the path's coming in and it's going horizontal. So the disappearance of water very rapidly and then the reappearance somewhere down slope is quite evident in these photos. And so the subsurface storm flow concept is a real thing. It's not something that was invented by some hydrologists to explain something they couldn't. Now, whether it's common all over the planet is a different story, but in these photographs, again, we have these vertical fracture features, if no other name, that could clearly let substantial amounts of water soak into the soil quite rapidly. And then here's a really big one. And so the question is, what's the hydraulic conductivity up here, over here, or right in this vicinity? I mean, you would think this is going to be huge because that's like a drain pipe. And that's all we needed on that. I just wanted to show those. So now the infiltration part, in my opinion, is complete enough to move forward with depression and canopy storage. So the video link doesn't exist yet. And let's go to the PowerPoint files. Good, that downloaded well. Okay, so this is today's topic, depression and canopy storage. And we're going to look at a few pictures and some conceptual descriptions of that. So here's a photograph. I'm not sure where it is, but it sort of looks like High Island on the Gulf Coast, although it probably is not. And we see this field here, and it has pretty substantial ponded water in it. And right in the deeper parts of the pond, there may be maybe upward as much as a foot of water depth, and then there's shallow parts, and then there's clearly land here. And this would be a hard situation to directly quantify. It's like whether we should treat that storage as if that's a reservoir, or we should treat that storage as just a specified depth beyond which water turns into runoff. And that's the whole idea behind depression and canopy storage. So we're back to our friends, the hydrologic cycle. I get a lot of mileage out of this slide. And none of what we're talking about today is really depicted on this photograph, on this sketch directly. But we're now talking about water that's going to be stored up in these tree canopies. So rain will come in and get captured by the leaves and stay there a while. Some of it will eventually fall through. I believe that's called through flow. And there's no pictures of little potholes here, but there are very shallow depressions on the landscape that can store water, and in some hydrologic computational situations we may want to quantify that. So I categorize these all under the concept of storage, but there's two different kinds. There's surface storage, which I have listed here as canopy storage and depression storage. And surface storage is typically treated as an abstraction, whereas reservoir storage, those are things like large detention basins, reservoirs, etc. Those are hydraulic elements. And not today, but tomorrow and Monday, we'll see how these hydraulic elements are manifest relative to an abstraction element. So this very busy slide is showing the rainfall-runoff process, and most of the processes we've discussed so far. In the HEC-HMS program, the watershed is something called a basin component. We'll get to that starting tomorrow. But we have losses, we have transformation, which we've not discussed in much detail. We have storage, and then we have routing. And when I say canopy and depression storage are treated as abstractions, that's another way of saying that they get put into the loss category. Whereas a reservoir storage, especially a large reservoir where you have known areas and depths, and you can make hydraulic statements about it, that if the water is 1 foot deep, there's 50,000 acre feet in storage or something like that. That's treated as a different kind of element. In the case of both the computer programs, they have slightly different names, but they're storage elements. And so our hydrologic story so far is we have precipitation comes in, and that's influenced by meteorology and climate. It falls onto the basin. The basin takes some of that input signal and flat out loses it, so we call those losses. It may take some more of the signal and store it. The transformation process is a way of understanding the temporal behavior between a parcel of precipitation that falls up here, the upper end of the watershed, and a parcel here that falls very close to the outlet. So we'll deal with that later. And then routing as water moves in these channels that are depicted here. And the ultimate output is runoff, and treated as a signal processing process. The runoff is the fraction of the precipitation signal that remains after all these other accountings are taken care of. So it's not unusual that there's pretty substantial rainfall doesn't produce very much observed runoff. And it's not because that's always the case. It may be that all these storage components were empty at the time of that particular rain. So here's a cartoon of canopy storage. It actually looks like a very small-scale hydrologic cycle to me because we've got our friend the sun that's driving everything. So we have precipitation comes on down. So here it's manifest as little teal water drops. And it hits vegetation, and it can hit bare soil. So let's follow the water drop that goes to bare soil. So it comes here out of the sky, hits the bare soil, and then it's presented with a choice. It can either become runoff or it can soak into the soil. Well, it's going to soak into the soil if there's soil capacity for it. So that's like the green amped model from yesterday. Once the localized soil can't take any more water, then the precipitation runs off. The water drop could also find its way into this vegetation, in this case a tree with very small, almost invisible green leaves. And a water drop can hit the tree, and the water has a surface tension, so it's not necessarily going to bounce off the tree and go onto the ground, but it may get held on the leaves and the branch structure. And then while it's there, it could evaporate directly back into the atmosphere, or it can be retained there for quite a while until more and more water comes in. Eventually, the leaves can't hold any more water under surface tension and whatever various physical orientation they have. And so some water droplets start to drop beneath the canopy. That's what I said. I think that's called through flow. And perhaps you've been out in a rainstorm, ill-prepared for it. I know I have. And if it's early in the storm, if it just started, you can seek a little refuge under a tree for a short period of time. I mean, eventually the tree won't be providing much, won't work as an umbrella very long, but it does for a little bit. That usually gives you time to decide which direction you're going to run next to try to keep from getting soaked. So that type of storage is called canopy storage. And we can even get to much smaller scale. So here's a flower and leaves, and they can hold a little bit of water, and then what's left makes its way to the ground. Oh, excuse me for that. So here's another picture of the same. Oh, it's called through fall. That was the word I was looking for. Precipitation is intercepted by the tree canopy. A portion of it is actually held directly on the leaves and may find its way back through evaporation. Eventually the through fall gets to the soil. Some of that is retranspired after it's infiltrated into the root zone. This whole behavior is treated as a loss or as an abstraction concept. And the portion of through fall that survives infiltration and some other processes eventually becomes our excess precipitation. So in canopy storage, interception is defined as the precipitation that does not reach the soil, but instead is intercepted by the leaves and branches of plants and the forest floor. The intercepted water generally evaporates and leads to a loss of precipitation for the drainage basin. And another way to picture the canopy storage is this cartoon here. So the red area represents perhaps a watershed. And the two little green areas represented the equivalent projected area of the vegetative cover. And then there's that's supposed to be a cloud, although it looks like one of those brains from Futurama. And the lightning bolts representing precipitation. The green areas intercept that rainfall and then process it. So they'll store some of it, and that which cannot be stored is then directed onward. And the usual approach is listed here, is that all precipitation is considered intercepted until the storage capacity is satisfied. Now the storage capacity of a tree in terms of depth of rainfall is not going to be very large. It certainly, in my mind, would be less than an inch. Then once that storage capacity is satisfied, the excess precipitation is then directed to surface or depression storage if there's any available. And then once the depression storage is satisfied, what's left over then can become excess runoff, and that's what we would eventually see at our gauge. We also would consider evapotranspiration as part of the hydrologic cycle in this kind of storage. It's a pretty sophisticated hydrologic abstraction. It's uncommon in engineering hydrologic applications, mainly because of the potential evapotranspiration feedback. It's going to have utility in scientific investigation. It's going to have a lot of utility in evaluating the merit of re-engineering large areas of a watershed in an effort to use these processes to enhance either the runoff quantity or quality. That's it's not new, but it's kind of emerging as a new line of engineering consideration for mitigating construction projects. So this is worth at least having a working knowledge of. To my knowledge, the measurements of canopy storage are practically non-existent, and in the past I've relied heavily upon agronomy literature. Someone's measuring it somewhere. There has to be some knowledge of that, but I don't even have a good idea how you would measure canopy storage. How you can make accurate measures of canopy storage. I suppose you could put a rain gauge up on top of a tree above the canopy, and you could put another gauge within the drip line at the base of the tree, and that would get you your through-fall, and the difference between the two would be what's in storage. So that's likely the simplest measurement, and then I'm sure there's expensive exotic techniques to answer that question. That'd be a interesting research study for somebody that wanted to do it and can find somebody to pay for it. So our next concept that's related, because it's often treated as an abstraction, is depression storage. And it's defined as the volume of water contained in natural depressions in the land surface, such as puddles. And Horton, who saw who? Where do you see an elephant? I get my Dr. Seuss mixed up. I like Horton as a hydrologist because it reminds me of a lot of Dr. Seuss books that I read as a child. And Horton, the hydrologist, had nothing to do with Horton in Dr. Seuss books. Actually, I think Horton was an elephant who heard a who. Anyway, okay, so moving back to the discussion. So here's a couple photographs. So these photographs, I obtained them by searching the internet using the search term prairie potholes. And so these are both aerial imagery. If you've ever flown into Lubbock, pretty much any time of year, but in the springtime it's pretty evident. And just after the springtime rains, and you look out as the airplane is flying towards the earth, hopefully under complete control, and you see all the way to the horizon imagery that looks like this right image. And as it gets closer to the ground, maybe like the left image. So the scale of these depressions, they're not very deep in a landscape scale, but hydrologically they are not insignificant. Hydrologically, they're significant. And a question emerges on whether I want to treat that as a reservoir, because if that's a farm operation, so there's a couple houses there, a barn, some storage, a place to fix all the machinery that converts gasoline into money. I mean, the area of that is fairly substantial. That could easily constitute a reservoir. And depending on our goals of our particular analysis, that may be a reasonable approach. Alternatively, if the scale of our question is much larger than the scale of this image, it may be quite convenient to just treat that as a depression storage term and uniformly apply some sort of storage behavior to our entire study region. So these pictures are what's meant by depression storage. So recall the green amp model that I hopefully just reviewed. In the green amp model, the water ponds at non-zero depth. For the green amp model to make any sense, there has to be some ponding above the at the air-soil interface. And so this depression storage is arguably very important for infiltration models, where we're interested in the infiltration behavior and not just as some generic loss. And the interaction of depression storage and infiltration is one basis of Hartonian overland flow. It's clearly a done saturation excess flow. The soil in this region right here by this large blue depression blob, where the cursor is hopefully moving around slow enough to be captured by the video stream, that's clearly saturated. And if additional rainfall occurs and this part here gets saturated, we would expect the water surface to increase the area of coverage. At some point, these ponds will connect to each other and create a surface flow path. So depression storage combined with canopy storage is somewhat of the usual approach. So here's Puffy the cloud making the rainfall signal, which I'm showing as a red arrow. And there's some sort of canopy storage, either depth or volume, that's assigned. And once that storage is satisfied, then there's spillover of the rainfall input. And I'm using a slightly smaller line to indicate that there's been some potential reduction in precipitation input, both volumetric rate as well as the timing of the occurrence. And then the canopy storage is then directed into the depression storage, which can be pictured as just a large tank. It has some initial storage in it. It has some prescribed maximum storage in watershed inches, maybe 2 inches of maximum storage. And then once the initial hits the maximum, any excess is allowed to become runoff. And that's a computational hydrology approach to making use of the concept of canopy and depression storage. If we look at it as a process diagram, so off to the right, we have precipitation coming in, we have loss models that act on the precipitation, and then what's left is excess. So the loss models that we normally have are evapotranspiration, which we've already discussed, infiltration, which is shown here in bold and large type to indicate that it's probably the most significant of these three, and then interception storage and depression storage, because they're considered abstractions, come in the loss model category. Reservoirs, on the other hand, are exactly what you think they are. A pond, lake, or basin, either natural or artificial, for the storage, regulation, and control of water. And that definition immediately brings into question, when does a depression storage become a reservoir? I guess the best answer to that is it becomes a reservoir when it matters to you for whatever questions you're asking of your hydrologic analysis. So if the behavior of that depression itself is important, it would make sense to treat it as a reservoir and then encode it as a hydraulic element in whatever tool you're doing. So reservoirs come in regulated and unregulated varieties. Regulation, by definition, just means that the outflow is controlled by movable gates and valves. So large water supply reservoirs are usually regulated. So we have the ability to open valves and let water out of the reservoir, usually in anticipation of a flood. And the head and the valve settings determine those outflow rates. There are also unregulated reservoirs, which are quite common throughout the U.S. at least, and the outflow of them is controlled by fixed weirs and orifices. In other words, there's no valving, if you will, on an unregulated reservoir. The head, or how deep the water is, and whatever the weir height, completely determine the outflow. So if the water in an unregulated reservoir is deep enough, it's going to leave the reservoir, usually by design, but you have no way of impacting how fast it leaves. It leaves according to whatever the hydraulics of the situation dictates. To quickly summarize, I told you today was going to be a short day. The storage types can be categorized as an abstraction type or a hydraulic type. The abstraction storage types are canopy and depression storage, and we briefly examined, in a very conceptual sense, what they are, and we will examine how they're encoded into a couple of the computer programs, and those will give you some insight if you ever have to do it external to those programs. If a need comes up, you want to deal with it directly. Abstraction storage, in my opinion, is a very sophisticated concept. It's going to be hard to estimate any parameters, and it's going to be hard to find measurements. I suspect that there's very few measurements routinely made. Nevertheless, if the hydrologic problem of interest depends on that abstraction, or you intend to alter the landscape to increase that type of storage, which is often considered in stormwater quality management and runoff mitigation, then you have to consider it and do the best you can to find measurements or estimate parameters, but it would be outside the usual hydrologic literature. Reservoir storage, on the other hand, is fundamental in any watershed model or any watershed consideration. Detention facilities are reservoirs. Best management practices, most of the physical ones, are some kind of reservoir. The other ones are filters, but they have a concept of a volume, so they behave as reservoirs. And reservoirs, Lake Skunk Depew with Lake Allen Henry, for instance, I mean, that's clearly a reservoir. The storage in that is going to be hydrologically important in its vicinity. And that was my main presentation for today. And we've got about 20 minutes. So we have a choice. We could complete the day and have a short day, which maybe is desirable for everyone. Or we can take 20 minutes and I will start on introducing you to HEC HMS. Maybe many of you have had it already, so the introduction will be just review. And then tomorrow we're going to look at each of these processes, the rainfall, infiltration, etc. processes, on how they are implemented in HEC HMS. I mean, we'll make up an example problem just to study the input-output structure. So why don't you all let me know if you want to move forward, and I spent about 20 minutes in HMS, which should take us to a reasonable amount of time. Or if you want to just have a short day. You don't all have to agree. It's up to any one of you, whoever chimes in first. Short day or move onward?
I say move onward just so that we could just do the review for the HEC HMS.
That's okay. I think I'll do that. And what I'll do for today, for the last 20 minutes or so, you don't necessarily need to try to follow along on the computer. I'm going to kind of do it as show and tell and take notes, and then tomorrow we will do it in an attempt to do it as an actual tutorial where there's follow along. So I want to find something on my computer that will make my life easier for doing this. So give me a minute to locate it. And now these files I'm about to grab, I will put them into tomorrow's lesson in the additional data. So even though today I'm going to get them from elsewhere, you're not going to have to go to these links. It's going to take me a second to find my way to where I'm headed. Homepage, server homepage. And I'm going to grab some file from, well, I'm not going to get anything because I can't actually get to it. All this fancy software is in the way. I think oh, I was hoping that was a directory. No, but I don't want that. I want to make sure I'm choosing the right example. Yeah, this will work. Okay. So I'm actually not going to try to grab these files. I should have made it as a zip directory, but I'm going to keep those nearby in case I get stuck. So what I want to do is go through the actual example. So this first example is how I would introduce HEC HMS to a brand new user who's never ever used it before. And if that's not you, just follow along. I mean, bear with it, treat it as a review. So I'm going to go to our portal here. We have success, and I am going to okay, example 4 was not what I wanted. I was just seeing if it was already there. Okay, so if we want to launch our HMS, if it's on your home machine, then you would just click on the icon or open it that way. And so here, since we're using the remote control machine, I'll use the launcher script. And there, definitely it launched it. So here's our fundamental HEC HMS interface. And if we're making a brand new problem, in the File menu, we're going to choose New. I'm going to name this one Ash Creek. Intro. So we may revisit Ash Creek, and I'll give you more background information on that. And my documents, I want to get it into the right place. This will be the most difficult part for you all, is you have to work through the file system. It won't let you attempt to write to the wrong directory, excuse me, to a directory that you're not an owner of. So I'm Hydro 3 right now. If I accidentally click on Hydro 5, it won't let me write to Hydro 5. So I want to go to Hydro 3. I want to go to my desktop. I want to go to my HEC HMS models. hopefully this is a new folder, and okay, so this is my opinion, is the hardest part of using this shared environment, is navigating the file system. Let's do it in US customary. Create, and now we have created a project. There's nothing in it. It's not very interesting yet. And now I've got to find where the example is. There we go. Okay, so we created a project, and now we want to simulate the rainfall runoff response of a single Texas watershed using, well, we'll pick one of these 3 loss models. We won't do all 3 today. There's not much to be gained from doing that. And we have an Ash Creek watershed, and so here's the problem statement. So we have a watershed outlet at Highland Road, Ash Creek, Dallas, Texas. Residential, White Rock Lake is nearby. So from this image right here, we could use the G3 data approach and determine the drainage area represented by that red boundary. It's going to be somewhere around 7 square miles. Now these units here might be unusual. So this is a UTM coordinate system on this map. And even though that map looks visible, that's really just a digital elevation model that's been rendered in shaded relief. And so these are in meters. And once you know that, you could easily take the whole area of the rectangle and then delineate the area on the inside and determine the drainage area to that outlet. We can get the precipitation from an old technique and make our model estimates from that, transformation model from that. This is what I want. We have these properties. So the first thing we're going to need is we're going to need to tell the computer program that we're going to have a drainage basin, and it's going to be 6.92 square miles. And I'm going to use curve number of 86. I'm going to use the NRCS method initially. So let's return to that. And so we have some components that we have to do. And a HEC-HMS model has to have a control specification, a meteorologic model. Let's have 3 things, and a basin model. So I'm going to select the basin model manager. We'll create a new one. We'll call it Basin 1 because I am not a creative person, but in a practical case, you may not want to you may want to actually name the basin. And so now you see here there's this basin model. And as soon as I select Basin 1, I get this drawing canvas. And in the drawing canvas, I now can choose these menu items. It doesn't have the Super Big Mac as an option, but there's a sub-basin creation tool. We don't need to make any changes here yet. We will when we attempt to run this thing. So let's go ahead and create a sub-basin. And I'm going to just use the default. So there's my sub-basin. So that's my first element. So that entire Ash Creek watershed is going to be represented by this single element. And when I select the sub-basin, I get data entry options for it. Looks like these 2 are identical. That's an unusual thing. What I'm after is put the 6.92 square miles. So an important observation here in the interface. The area has a red asterisk next to it. That's the computer program's way of telling you that item has to be specified. It can't be left blank. The other stuff can be left blank and dealt with later. I want to make a couple of other changes. I'm going to choose the SCS unit hydrograph, which we haven't discussed at all yet, but we'll get to it. And I'm going to choose my loss method as SCS curve number. And base flow is going to be none. Okay, so this is a pretty basic watershed model. So right now we have a watershed that comprises a single basin. The loss method on that basin is the SCS curve number, and the transform method on that basin, which is to handle the time change for a raindrop that falls very far from the outlet compared to one that falls very close to the outlet, is the SCS unit hydrograph model. If we choose the loss tab here, we can give some information on that. I'm not going to do that just yet. We also have some options here. We could deal with canopy storage, and we can deal with depression storage. Right now I'll leave those as none. We will change that later on. Maybe not today, but in a future part of the example. All right, so we've created a basin. And oh no, you can't sit on the keyboard. My cat has decided to totally get in the way today. Okay, so there we are. We got the basin. Let's return to the example. So curve number is 86. I want to go ahead and insert that value in the loss model. And currently we've set the percent impervious as default to 0. And what that means is that the entire 6 square miles is treated as if it has curve number 86. We could change that to represent our best estimate of the impervious cover. In the case of the curve number method, if we choose to do that, we don't necessarily want to be using a composite curve number that includes impervious area, because then we'll be double counting it. It will run, it'll produce numbers, but they'll be goofy or meaningless. And then we can supply an initial abstraction, which I'm going to leave blank. So leaving it blank sets it to 0. But if you have knowledge that the first inch of rainfall, for instance, never becomes runoff, you can abstract that directly from the input signal. These other pieces of information are useful when we're using a different loss model. So we're going to need a hyetograph. We've got loss model parameters. We don't have a transform model parameter yet. We'll take it off of this example. So, the hyetograph's been generated. We have some choices on that. We create our meteorological model. It has to have one, so we'll call it Met1. And here it's asking, how are we going to represent precipitation? So we have some choices. Frequency storm, gauge weights, specified hyetograph, standard project storm. I'm going to leave specified hyetograph. Hopefully I can find a time series and get it into the software easily. So the data has been prepared. And so we're going to use a, I'm skipping through a lot of the example, we're going to use a time to peak of 85 minutes. So we'll go ahead and supply that to the computer program. That's a subbasin property. Transform 85 minutes. Leave that be. Hit save the project. And I'm looking for a input rainfall. There we go. Okay, we will attempt this. This may be a complete failure, but let me see if I can find some rainfall input. Oh, it doesn't, just metadata. With any luck, it has been left behind, so we'll be able to capture the input time series. This is the second hardest part of input. I'm actually not going to use it all. I'll prepare the files for tomorrow's demonstration. So we're going to use a different kind. We'll use a frequency storm. So I'm going to pick a particular type of storm. Remember when we were talking about design storms? I'm going to use what HEC-HMS calls a frequency storm. And in the rats, we used to have the SCS type storm in it. That's really what I want to get. Good. Specified standard project storm. Nope. Bingo. Okay, so it's now called hypothetical storm. Used to be called SCS storm. This is in Texas, so it's probably a type 2. And we'll use 6.9 inches. Area reduction factor, we'll leave it at none. And our meteorological model is defined up to a point. We also have to, in the meteorological model, we have to tell it to associate that storm with the subbasin. Tomorrow we'll go through how to actually use actual time series. The next component we're going to need is in meteorological control specifications. And this is one of the parts I find infuriating about HEC-HMS, but infuriating is irrelevant. I have to live with it. You have to put in calendar dates. I'm going to start on 1 June 2020 at 00:00, and we'll go to like the 4th of June, 04 at 00, and we'll do 15-minute time interval. And we still don't have a run control. Okay, my knowledge of HEC-HMS, this is sufficient to run a model. So what it's going to do, it's going to use an SCS type 2 storm. It's going to apply it to this subbasin. That's going to be converted into direct precipitation input. Then the curve number loss model is going to be used to reduce that input to excess runoff or excess precipitation. The excess precipitation is going to be transformed by an SCS unit hydrograph with an 89-minute lag time to the outlet to this subbasin. And once we build a proper run, we can have it calculate what the hydrograph, the direct runoff hydrograph, would look like at the outlet to the subbasin. So to do that, we have to create a simulation run. And I am interested in select a meteorologic model. Let's see what happens. Okay. Yeah, it looks like it has all the correct specifications. It just didn't show them to us. So if I select the run specifications, so Basin 1, Meteorological Model 1, Control 1 are going to be used. I'll attempt to run it. We can run it by clicking on this exploding raindrop, or we can run it up here from Compute Run. There's a reasonable chance I've missed something. So this messaging area down here in the drawing canvas will issue warnings and error messages. And from those, it's pretty easy to deduce the missing input. So let's give it a shot. Simulation end time is not an even number after the start time. So if you look at, I have an error in the start time entry. It says I entered 2022, which isn't going to occur for another 19,800 years. So we'll go fix that. So we'll close this, go back, go to the control spec, and we'll attempt to run it again. Okay, begin computing. No area is set for subbasin 1. So let's go to subbasin 1. It's supposed to be 6.92 square miles. Don't know how I missed that. May have forgotten to save it. Hit save. And we'll try again. Okay, in this case, there were no warnings or errors, so that was a successful computer run. And that's pretty typical in building the model from scratch, is you have to go through a few errors to correct little input errors. And once you have a working one, that's where I usually start to try to adapt it to the problem I'm really interested in. And so to view results, I right-clicked on the object. Go ahead and pick graph. And what it should show me is, here is the outflow hydrograph. I have real data for this watershed, so later on we can examine real data. But again, I need to pre-place the files. And the blue here is the precipitation. The red is the loss component. And so the difference between blue and red, if you integrated it over time, it would have the same area as under this curve. The difference in peak here for the storm and the peak here should be roughly an hour and a half. So that's at noon. And this peak is showing up now, is at 13:32. That's an hour and a half. So this is the simple introduction to HEC-HMS. Now what we're going to do is we'll probably use the Ash Creek watershed as a study watershed. We will increasingly add complexity to the model to explore the different parts. So in about 1 minute if we were to take a simple Canopy model, we choose yes. Then we would have to, initial storage 0. We'll let the Canopy store up to ½ an inch of rain, which is ridiculous, of course. And we'll have the uptake method set to none and evapotranspiration only during dry periods, which will ignore, there's no dry period in this simulation. So we made that change, update it, let me try to rerun it, and I want to move the slider up once it'll let me. So we reran it again, and there were no error messages or warnings. I can't see a difference in the output, but at this point we've now included a Canopy model. If we want to include surface storage, I'll pick simple surface. None of the gridded stuff will work for us because we don't have this attached to a geographic information system. Let's set the initial surface storage at 0. And let's suppose depression storage in that 7 square mile watershed that it can store, I'm going to be ridiculous, we can store 2 inches of water. Now I expect we're going to get a change in the output because the loss component is going to increase quite a bit. But I will know that when we actually make the run. Yeah, look at the difference in peak discharge. 4,000 cubic feet per second has been abstracted into surface storage. That's with 2 inches of storage, and that is intentionally ridiculous. So that is a introduction to this tool. Tomorrow we'll go through a lot of this again, but in much slower detail. So have a good afternoon, everybody. Thank you for your patience and attention. And I'll get this video rendered and put up. What I'll be doing between now and tomorrow is I will prepare some necessary data files. I think I'm going to put them in Hydro 1 through Hydro 5 ahead of time so that they're already there. And I will, I need to prepare the second exercise set. I have it more or less ready. I want to check that I've typeset it correctly. And again, there's going to be no hurry on that. I'm not trying to crush you all with homework, but it's useful to do a little bit each week. So again, thank you. See you tomorrow, and have a great day. If there's any questions, now's a good time to ask because I'm about to end the meeting. Very good. Okay. I will see you tomorrow. And I will also go tomorrow. I will go through, if you want to install HEC-HMS on your personal machine and not use the share space, it'll run faster if you do that. I'll put some videos up on how to do that. It's not that hard for a PC. It is hard for, it's actually impossible for a Macintosh thanks to the new operating system.